right, well today we're going to do sample exam number 2 review. Today is Monday. The exam is Wednesday. We're in D204 for the exam. Again, 3x5 card. There will be a periodic table attached. Tutorials in quiz 2 must be done. And please bring a calculator, especially in the D building. I'm really not sure if there will be calculators. Any questions before we get started? Okay, let's do this. It's going to be a short lecture just like last time. And that's to stress to you just how easy this is going to be and put you at ease, right? Right. Question 1. Which of the following are the name, formula, and water solubility properly matched? Iron 3 chloride. Most metal chlorides are soluble in water, except for the heavy metals. Iron doesn't count, but the formula here is wrong. Chloride would be -1, making each iron plus 1.5. Doesn't work that way. FeCO3. Ammonium sulfate. If it's an ammonium salt, it will be soluble. That's good. But this is hydrogen sulfate, first of all. That's a -1 charge. Ammonium is +1. Doesn't work. Calcium sulfate. Sulfate is -2. Calcium is +2, so the formula is right. But most sulfates are soluble, but calcium is one of the exceptions. Aluminum chloride. Most metal halides are going to be soluble, so soluble works. But the formula here is nonsense. Aluminum chloride has 1 aluminum and 3 chlorides. Finally, it must be this one. Mercury 2 chloride. Chloride is -1. That's mercury 2. Insoluble in water. Yes, it is. Any questions? Number 2. We are doing a double replacement reaction here, taking copper 2 sulfate and barium nitrate. Mixing them together, we want to know what we get. Remember, in a double replacement reaction, all you're going to do is swap ions. You don't do redox, you just swap ions. So copper will pair with nitrate, barium will pair with sulfate. Excuse me. Most sulfates are soluble. Barium is one of the exceptions. It is a solid. Number 3. Balancing an equation. Yes, you will get to balance an equation on your exam. Let's just look at this guy. We have 3 oxygens here, 2 on this side. Let's make it even by doubling that. Now, when we do that, that gives us 4 irons. 1 on this side. Let's change that to a 4. We also introduced 6 oxygens. When we did this, we only had 2. We need a 3. And finally, by sticking our 3 in here, we need 3 carbons. And by George, I think we balanced the equation. Now, on the exam, just like on Blackboard, if a coefficient is 1, put a 1 in the blank. Any questions? Single replacement reaction. In a single replacement reaction, an element and a compound react to form an element and a compound. Which element? Well, iron is going to replace copper in the copper nitrate. Copper will be our new element. Quite simply, Cu. Any questions? Number 5. All right, which is not a redox reaction? Now, there are 2 ways to do this. One is the old-fashioned slow way, and the other is being clever. So let's do it the old way first. Nitrogen, hydrogen are both elements. By definition, they're 0. And the products here, hydrogen is bonded to a nonmetal. That makes it a +1. We have 3 of them. Make it neutral. Nitrogen must be -3. Now we can do that for all of them. But you can look at it and just figure out a pattern. The pattern is this. If you have an element, either in the reactants or the products, that element is going to be 0. If it's in a compound on the other side, that's redox. So, we look at this. Element, compound. Element, compound. Element, compound. All of these, 1, 2, 3, 4, are redox. So let's look at the one that isn't. Oxygen is going to be a -2, just by default. We have 2 of them, making this nitrogen +4. Over here, oxygen is still going to want to be a -2. We have 8 negatives here. Each nitrogen must be +4. No redox. Any question? Number 6. Another redox question here. We have chlorine going to chloride. Chlorine is an element. It'll be 0. Chloride's a halogen. It'll be a -1. All right. We remember oxidation is loss of electrons. Here, chlorine has gained an electron. Since it has gained an electron, it's a reduction. Everyone good with that? Number 7. Okay, this is a hypothetical reaction. We're taking 2 A's, 2 B's, 6 C's, making 4 D's and 3 E's. We are given 2 A's, that's what we need. 3 B's, We only need 2. 6 C's. That puts the B in excess, doesn't it? 5. The limiting reactants are going to be A and C. So basically, this is going to go just as written. So, hey, 4 moles of D will be formed. Yep, that looks good to me. 2 moles of D will be formed. It can't be both 2 and 4 at the same time, can it? 3 moles of E. Yep, that's going to work. And that makes it an A and C. Are we good? Good. Number 8. We have 1 molar solution of calcium nitrate. We have 0.3 liters of it. How many moles do we have? Well, we have a concentration and a volume. 0.3 times 1 gives us 0.3 moles of calcium nitrate. Okay? 0.3 moles of calcium cations. If we look at our formula here, the mole ratio of calcium to calcium nitrate is 1 to 1. If we have 0.3 moles of calcium nitrate, we also have 0.3 moles of calcium cations. Once again, we're looking at nitrate now. The mole ratio is 2 nitrates for every calcium nitrate. If the mole ratio is 2, we will have twice as much. And this is an ABC. Number 9. We have potassium chloride reacting with silver nitrate to produce silver chloride. We look at the stoichiometry here. It's a 1 to 1 to 1 to 1, isn't it? Can't be much simpler than that. If we had 1 mole of each of these, we would get 1 mole of silver chloride. But we don't. We have half a mole of each. If we have half a mole of each, we would get half a mole of silver chloride. Next choice here, 143 grams of silver chloride. Well, this is the molar mass of silver chloride, 143 grams per mole. 143 grams would be 1 mole. So that's wrong. It's half a mole. 1 mole of product will be formed. Nope. Half a mole will. Potassium nitrate will precipitate. Nope. Nitrates are all soluble. It's simply A. Any questions? Well, we kind of did this in lab, didn't we? We took sodium hydrogen carbonate, heated it up, got solid sodium carbonate, CO2, and water. In this particular experiment, 0.25 moles of CO2 were collected when we started with half a mole of sodium hydrogen carbonate. Now, the stoichiometry here. 2 moles of sodium hydrogen carbonate give 1 CO2. So half as much. If we had 1 mole of this stuff, 2 of these, we would get 1 CO2. 1 of these would give us half, 0.5 would give us 0.25. By George, that's what we got. That's 100% yield. Now, many of you got like 103%. That's good. That's good. Any questions? Okay. We have half a liter of 1 molar nitric acid. Concentration times volume, this is half a mole. We want our final concentration to be 0.5 molar. 0.5 molar means 0.5 moles per liter. So we're starting off with half a liter and it's 1 molar. We are going to add water to it. Half a mole per liter. Start with half a liter, so we have to add what? Another half. Bring it up to 1 liter. This is half a mole in 1 liter. This is a very simple little calculation. We have 0.375 moles of solute, doesn't matter what it is, and our volume is 1340 mils. What's the concentration? Well, we either look at our little card, or we just remember. The concentration is going to be moles divided by volume. The volume must be in liters. So we have to convert this to liters. Simple, divide by 1,000. Concentration, let's substitute. 0.375 divided by 1.34. Do the calculation. It's 0.280 moles. We're running 3 significant figures here. Everyone good with this? pH. pH always gives people problems because it's kind of like backwards. But okay. We have a solution that's at pH 5. We increase that pH to 7. What happens to hydronium? Well, remember, if the pH increases, hydronium ion decreases. pH goes up, hydronium goes down. So we're looking for decreasing. Secondly, pH is a log scale. We're talking about the exponent here, 10 to the x. We have changed it 2 units. Therefore, the exponent is 2. 2 pH units, factor of 100, decreases by 100. You can also do this in your head, if you like. At pH 5, we are 10 to the minus 5 hydronium. At pH 7, we are 10 to the minus 7. That's a factor of 100 less, isn't it? Good question. All right, let's do a chapter 11 problem. We have selenium 80. It loses an alpha particle. That means the mass number is going to drop by 4. The atomic number will drop by 2. So we pull out our periodic table, find selenium, take 2 off the atomic number. Let's see what element we're at. Selenium is right here. Atomic number is 34. We lose 2 protons from the nucleus. We're down here at germanium. This drops by 4. So we're looking at germanium 76. Any questions? This is one that everybody or lots of people get wrong. So think about this one. We have 1 liter of half mole of sodium hydroxide. We have 1 liter of 0.5 molar HCl. We're going to mix these. Now these are equal concentrations and equal volumes, right? So when we mix them, the strong acids, the strong base, we will wind up with a neutral solution. So number 1, the solution will be neutral. Well, it can't be neutral and basic at the same time, can it? So that's why. This is the thing that gets people confused. Is the concentration 0.25 molar or 0.5 molar? Well, what we have done here, if you want to do a simple calculation, concentration times volume, that's 0.5, this is 0.5, but our volume now is 2. So it's 0.5 divided by 2. The volume is doubled. We have half a mole to work with. That's correct. It's an A and C. Everyone good with that one? Here we are given hydroxide concentration. We want to know what the hydronium ion concentration is in that solution. We can do that because we remember, or we have written down somewhere, hydronium times hydroxide is always a constant at 25 degrees centigrade. 1 times 10 to the minus 14. So, all we have to do is substitute in our value for hydroxide. Then we're going to divide 10 to the minus 14 by 10 to the minus 5. When we do the calculation, we could do it in our head. 14 minus 5 minus 9. Any questions? All right, which of these are acidic? pOH is less than 7. Well, if the pOH is less than 7, that means that pH must be greater than 7, because pOH plus PO plus pH are always 14. So if pOH is less than 7, pH must be more than 7, making it basic. That's all. Hydronium times hydroxide is less than or equal to 1 times 10 to the minus 14. In the previous problem, I stated this is always exactly equal to 10 to the minus 14. So that's one. OH is less than hydronium. Well, if OH is less than hydronium, that means our solution has more acid than it does base. That makes the solution acidic. Any questions? All right, number 18. Gas law problem. Sealed cylinder, movable plunger. We increase the pressure. What happens to the volume? This is a Boyle's law problem. If we increase the pressure, pressure and volume are inversely related. So we increase pressure, we decrease the volume. Questions? Of course, Charles comes next. Temperature increases. What happens to volume? Remember our poor little balloon? Charles said the two were directly related. Temperature increases, volume increases. So we have increased our temperature, we will increase our volume. And number 20. We are at 100 degrees centigrade. What is that in Kelvin? Remember the relationship. First of all, Kelvin is always larger. It's larger than centigrade by a factor of 273. Centigrade plus 273 is Kelvin. 100 plus 273 is 373. And then finally, the long-awaited extra credit. We are going to draw the structure of 3,3-diethyl 2-methyl-hexane. On your exam, I will tell you now, because I've written it, you will be drawing a structure. So make sure you get this, okay? We start at the end of the word with hexane. Hexane, 6 carbons. So we start off with a zigzag with 6 carbons. 1, 2, 3, 4, 5, 6. We are going to define one end, doesn't matter which one, as carbon number 1. Now we have substituents at carbon 2 and 3, so let's number those. At carbon 3, we have 2 ethyl groups. Ethyl group is 2 carbons. So we have 2 carbon units right here on carbon 3. We draw them in something like this. It doesn't matter which way these guys point or what angle they're at or whatever, because they are rapidly moving, remember. On carbon number 2, we have a methyl group. Methyl group is a single carbon. So we start here, we go up with a simple line. And this is 3,3-diethyl-2-methyl-hexane. The structure you draw on the exam will be comparable in difficulty. Everyone got that? Also make sure from chapter 12 that you remember the hybridizations. They're on there. And on there, chapter 11, make sure you know particles and stuff like that. And then make sure you know everything else. Any questions? See how simple this really is? It's still only 2 o'clock. Exam is Wednesday, D204. Please be there, be on time. You have 60 minutes for the exam. It's not at 2 o'clock. Sorry, it's at 11. You may bring 1-3-5 card, periodic table. I will give you tutorials. Quiz 2 must be done. Make sure you have a calculator. Here's our list of tutorials. And remember, we are shooting at 350 points. If at the end of exam 2 you have over 350, even 349, you will get an A in the course, no problem. Everyone good with this? If you came in late and didn't put your exam down, please do. Have a good day, and I will see you on Wednesday. Hold up, Jerry. Eduardo, did you, if I could look at the testing set?
Yeah, they're gonna correct they're gonna correct them.
Okay. I will just send the form with the date and the funding.
Yeah.
Okay.
Use the